Welcome to the dynamic learning hub of XLR at Andheri East. A prime spot conveniently located at just a 5-minute walk from LIC Andheri Metro. In our journey of over a decade, we have proudly trained over 2 lakh students. We have also been recognized by Deloitte, Silicon India, and other accreditation bodies. Experience learning like never before in our spacious and comfortable classrooms. With high-definition projectors and state-of-the-art acoustics in place, we ensure effective learning even to the farthest point in the room. A hybrid mode is a game changer as you can enjoy the benefits of a light classroom from the comfort of your home. Even if you happen to miss any classroom session, you can still attend the same session with the same trainer at the same time at your convenience, maintaining consistency in your learning progress. Wanna get started? Join us for a demo or career chat over a cup of coffee at our Andheri branch. XLR. We don't just train, we build careers.
Yes, so the collaboration with XLR was an excellent one. We conducted a Power BI workshop with Advanced Excel over a span of 3 days. The workshop was almost 12 hours long in total. Mr. Karthik, who was an amazing trainer, helped the students understand the concepts deeply. I am sure that the students will be able to apply these concepts in their careers as well as their daily lives.
The trainer, Mr. Karthik, was an excellent person where he explained in very detailed manner on how to give great insights using very complex data sets.
So it was a machine learning workshop. We learned a lot from the course and it was a great experience attending the workshop.
The trainer was very helpful. He had a hands-on approach with his teaching and it was fabulous.
This was a great experience for me. So I would absolutely love it if XLR and its team would come again to our campus and conduct more events like this.
It was a great course and it started from basics and took me to a great extent.
The experience of the workshop was really nice. The feedback from all the students was positive. They understood the concept. The workshop was also practical based with some questions. The experience with XLR was very smooth. They helped us in conducting the workshop smoothly right from the booking of the vendor and deciding the course till the distribution of certificates. In overall, this workshop was a success during our Technical Fest Atmos, and I thank XLR for being a part of it.
very much interested in learning digital marketing course for a very long period of time, but I don't get a proper platform. So later for my college, I get to know about XLR and I enrolled in XLR course. It was really good experience. Our course has been taken by Mayur sir, and he was very good teacher. He not only focusing on theory part, he's doing how real digital marketing works, and it was in total very good experience. I get so much of knowledge. Here they're not only focusing on study, they're also conducting different exam to test our knowledge. And as we are giving the exam, so to appreciate our work, they give certificates for the toppers, and along with the certificate they give hampers. Thank you, XLR.
Recently, I was searching for digital marketing courses online in Google, and I came across XLR, and I attended a digital marketing course which was for 15 days. My mentor Mayur helped me for attending these classes. So he is a very informative and helpful guy. In the course end, there is a exam which I topped, so I came to the XLR office in Bengaluru. This digital marketing course has helped my career and my skills to develop, and the certificate has helped my company to join. Thank you, XLR.
I came to know about college. Actually, for learning platform, this is very nice, and I learned from here ChatGPT and AI from online. Because he's teaching for me for AI generative and ChatGPT. We are using this technology in more.
Good afternoon, all. I hope you are doing well. So today is the last day of this particular program. Okay, we'll start with the session. Good afternoon, Amrit.
Good afternoon, Sushmita.
Yeah, you can start the session, sir.
Okay. Okay. Good afternoon, all. I'll share the screen first. Just a second. Okay, so today is the day 5 of our quantum computing course, and today we will be focusing on the topic quantum computing applications. So for the last 4 days of the course, we discussed about various aspects of quantum computing, starting from the quantum dots, or rather qubit, quantum bit, and how to implement qubit in reality in its simplest form, and that is in the form of an electron. And we learned about how do we represent qubits in various abstract ways, such as in vector spaces, in the form of matrices, and also as points on the particular block sphere representation. And on the day 2, we discussed about the basic mathematical formulations, such as how do we represent multiple qubit systems in the form of tensor products, how do we implement various quantum gates on this special quantum systems, and they are fundamentally different from classical gates, as we have seen, where classical gates are composed of AND, OR, XOR gates, etc. In quantum scenario, we have gates such as X gate, Hadamard gate, um, C0 gate, where the fundamental operation is different from that of classical. For example, the Hadamard gate is used for making a superposition of states, and it has no other classical analog because there is no concept of superposition in classical systems. We also see the concept called entanglement, where two particles which are far away can be interlinked with each other, can be sort of exchanging information with each other. And this property of quantum systems can be utilized to securely transfer information from one point to another point. And we also saw a practical implementation of it in the form of quantum teleportation, theoretical. And on day 3, we delve more into the theory. We delve into the various quantum algorithms which have got significant advantage over the classical systems, and also a little bit of software implementations of them in the Qiskit SDK. And day 4, we learned about hardware quantum devices, where we had discussed about 4 or 5 implementation of or physical realization of the qubits, such as the quantum dots in the semiconductor in the semiconductors, where we can leverage the advanced cutting edge semiconducting microfabrication technologies to design qubits and NV centers in diamonds. Thirdly, superconducting qubits, and also ion traps and neutral atoms, which all of them have advantages as well as disadvantages in designing a qubit microchip, which has the ability to integrate multiple number of qubits, as well as mitigate or correct the errors that incorporate in them, also to maintain the quantum state for a longer time. So all these considerations are at the forefront, in the limelight for designing a qubit microchip using these platforms, and further research is underway. So with that background, today we are discussing about the applications of the quantum systems or quantum computing, in other words. And when we speak of the quantum computing applications, one of the recent breakthroughs that has happened in this field is none other than the invention of Microsoft in the form of Majorana 1 chip. And this has been a result of a very long experimentation and research activities, focusing on a very unique platform, which is very different from all the hardware implementations that we have seen in the last day. Physics is qubit system, and the sorry one of the main advantage of using this particular physical realization of Majorana 1 is that this chip can integrate a million qubits in a single chip. And this has not been possible in other systems like the superconducting qubits and quantum dots, where addition of qubit or the scaling of the chip as or on the chip
Request kindly wait. I think there is some network issue. Please wait for a while. He'll join back. Dear faculty members, the trainer is facing some network issue. He is going to join in few minutes. Please be waited. He is joining back. I request, please be waited for 2 more minutes, 2 to 3 minutes. He will join. Yeah, I'm so sorry for this inconvenience. Like the trainer is going to join, is facing some issues in his system. So I request you all to wait for a few more minutes. Please be waited. I know you all joined and you're all waiting. Please, we are so sorry for it. Please be waited for a few minutes. He'll be joining back.
Hi all, I'm back. Sorry for the technical glitch. There's been some issue with the internet. I'll share now and we'll resume our session. Okay. All right. So today we were discussing about quantum computing applications, and the first topic that we would like to discuss is the Microsoft's Majorana One chip. And this is a very unique breakthrough because of the type of architecture they have used in this particular chip, or rather the physics principle that has been used to make this chip is something very unique, and that is the topic of or the concept of topology. And in this connection, a particular state called Majorana bound state has been involved. And to understand about this, we need to understand a very deep, very basic concept that's coming from the mathematics, and that has implications in physics. And this is called the Berry phase, or the topological physics. And the speciality of this particular topological qubit implementation is that at the hardware level itself, the error correction is carried out, and thus there is no need of attaching a hard error correction module to your architecture, and that would save a lot of complexities and will help. So in the early 1900s, an Italian scientist named Ettore Majorana, he introduced the Majorana fermions to the world, and he had a vision of um, this Majorana fermions being used in high energy physics, where particles with very high velocity, they collide and generate new particles which are fundamental to various universal phenomena. And in the high energy physics, there are two terms, that is a particle and antiparticle. And for every particle, there is an associated antiparticle, such as for an electron, you have a positron. And for something like a muon, it has got an associated antiparticle. So for every particle has got an antiparticle. However, there are certain systems having the same particle acting as its antiparticle. So that is represented in mathematics in the form of gamma, same as gamma dagger, where gamma is the particle and the antiparticle is a gamma dagger. So the symbol is the dagger symbol for representing the antiparticle. So if you consider two electrons, such as this, C and C dagger here, so these are representations different from what we have used for particle and antiparticle. This simply mean that we are using a second quantized formalism, and so it is second quantization. So in the second quantization formalism, we generate particles and annihilate particles. It means that we have a particular representation of writing the system, writing the description of the system, where a new particle, where we represent a notation for uh, stating that a new particle is generated in the system, or it has been it has been introduced into the system, and a particle, an old particle which is already in the system, it has gone out of the system. So for that we write C and C dagger, and these have got names. C is called as the annihilation operator. And C dagger is called the the creation operator. Annihilation means destruction, and C dagger is the creation operator, where the particle is generated. So I represent two electrons here, where one represents that an electron has been created in this particular site here, and another at another site, the electron has been removed from the system. So that I have represented as C. So a filled circle represents the presence of electron, and an empty circle represents the absence of electron. But when I have a system such as gamma equal to gamma dagger, whose antiparticle and particle are the same, then I can have a description such as this, where there is a superposition of both electron being absent and electron being present, such as a half-filled circle. So that is the property of the Majorana fermions, which was discovered by this gentleman, Ettore Majorana. And we can express this understanding in a mathematical form, such as given here, where gamma 1 and gamma 2 represent two Majorana fermion particles, and they are written in terms of 1 by 2 times C plus C dagger, where C is the annihilation operator of the electron, C dagger is the creation operator of the electron, and gamma 2 is another Majorana particle, which is the pair of gamma 1, and it is written as I by 2 times C minus C dagger. And these particles called Majorana particles, they cannot come in a single system, as in a single, they always come in pairs. So we can express the operators of electron, the C and C dagger, in terms of the Majorana fermions, such as this gamma 1 plus I gamma 2 and gamma 1 minus I gamma 2. And you can, as an exercise, you can check whether the gamma 1 and gamma 2, they have the relation, such as this gamma equal to gamma dagger. So one thing I missed out is saying that the gamma dagger, which is written here, this represents the complex conjugate as well as transpose. So you take the complex conjugate and in the case of matrix representation, you have to take a transpose also. And this is also called as Hermitian conjugate. So rather than writing complex, I can simply write it as Hermitian conjugate here. So that is a property of particles like Majorana, that they have the same Hermitian conjugate and they have the same antiparticle. Now, the crucial point here is the topological protection that is offered by these Majorana particles, or rather Majorana states. In the field of condensed matter, although the Majorana particles were discovered in high energy physics, they have immense potentiality in the field of condensed matter physics. So that is where we are trying to build quantum materials that can be used for implementing qubit systems or physically realizing qubit systems. And in the condensed matter, we don't have any strange particles arising, just as in the case of high energy physics, where you have particles like Higgs boson, quarks and muons. We don't have such particles emerging out from the metals or semiconductors or insulators, but rather we have signatures of bound states within these materials, which have kind of analogies to the kind of particles and states found in the high energy physics. So what we find in the condensed matter world is the formation of Majorana bound states, which are formed within a material having certain properties and under certain conditions. And a crucial condition is that of a particle hole symmetry, or rather one of the crucial conditions is particle hole symmetry, and which can give rise to these Majorana bound states. So as I say before, the electron, when electron is present, a superposition of electron being present and electron being absent, right? So I can represent it like this. So this superposition is a genesis behind Majorana fermion being being present in the system. So Majorana fermion exists in a superposition of electrons' presence and absence, and for that, a particle hole symmetry is required. Means that electron being present means you have an electron in the system. When electron is absent, means that you have a hole in the system. You have a hole in the system. And when which material or which family of materials have this kind of a property, where there is a symmetry between the electrons and holes in the system. We know from the band studies or the solid state physics that we can represent the valence band and the conduction band. This is the valence band and this is the conduction band. And when these two are having a symmetry, between them, which means the features of conduction band exactly matches with the valence band, and there's a rule of them to be same, equivalent, or there's a mirror symmetry in the xy plane. And such a situation is a case of particle hole symmetry, where it simply means the electron and the hole, they have a kind of a symmetry. Their energy dispersion follows a symmetry. And we find this kind of symmetry in materials called superconductors. So superconductors are materials in which the electrons, or rather the charge carriers within the system, they form an condensate, which is very coherent condensate, and and it carries out lossless transport. And they have superconducting gap within the materials in the form of symmetric band states, where the bottom one is a negative energy corresponding to the hole, and the top one is a positive energy corresponding to the electrons, right? So rather, here there is a superconducting gap here, which is the delta, superconducting gap, and they follow this particle hole symmetry, in fact. So okay, and there are two kinds of superconductors. One is a trivial superconductor, and the one is a non-trivial superconductor. So the Majorana fermions uh, are to be found in the case of a non-trivial superconductor, not in a trivial superconductors. However, most of the materials that we encounter in the world are that of trivial superconductors, and very few are non-trivial, and there are questions or debates surrounding those non-trivial superconductors. To achieve this Majorana particles, there's one particular understanding that we know that electrons are here in the top and energy, and holes are in the negative energy side. However, the Majorana states, they have same antiparticles. They have same antiparticles, and that will imply that they also have same energy. And when both of them are having the same energy, both antiparticle and particle, it is only possible when they are at the zero energy level. Because if suppose the Majorana particle, let's say it has a positive energy, then the antiparticle will have a negative energy, and thus they are not equal. Hence, the energy of Majorana particles are supposed to be E equal to 0. And this is the topology I was mentioning about, that to maintain this E equal to 0, they will have a protection ensured by the topology. Something similar to what we see here, where you have a cup with a hole in it, right? Now, if I try to deform this cup by applying some pressure, taking it to some mill and applying some pressure, not such a way that it doesn't break, but rather it deforms in a tensile way. Then the question is, can I make this this particular object by deforming this cup? What would be the answer? Obviously, it is a big no, right? Because no matter how carefully I deform this, the hole will remain in the system, even if I change the shape in any manner. But in the case of this particular glass, there is no hole in it. There is no hole in it. So I cannot deform this cup into this glass. But what about this particular system? Which of these two can be deformed into this one? So for that, we need to carefully analyze the structure of this cup here, or this glass here. So if we analyze this, we will see that this glass also does not have any hole in it. So we can make this glass from this particular glass, not from this cup. So we can make from this one, but not from this one. So that is because the topology of this cup is different from the topology of this. However, these two have the same topology. So I can deform it into this one. Same way, the topology of a material having the Majorana particle at equal to 0 is protected in a similar way. So I can say that this kind of transition from here to here, it is not possible. It is prohibited because of the topology. So in the same way, I cannot transition from a E equal to 0 state to some E equal to non-zero state because it is topologically prohibited. All right. So now at E equal to 0, I can not only have one particular pair of Majorana, but I can have multiple pairs. And these are all degenerate at the E equal to 0 state. So there will be, if I have n pairs of Majorana, then I can have 2 to the power n fold states of Majorana at the E equal to 0 state of the superconductor. But now the question is, from the, I have very few trivial conductors, superconductors in the nature from which I can make the Majorana, or I can observe the Majorana state. So how do I go about to see actual Majorana states? Can I use a vortex state in the superconductor? So what is that? If I have a superconductor and it is a high TC superconductor, which means it is not following the traditional BCS framework. Rather, it has a high transition temperature, which is uncommon for BCS superconductors. And they have also two transition temperatures, the TC1 and TC2. And within the window of TC1 and TC2, they host vortex states, which is flux lines of magnetic field penetrating through these superconductors. So when I apply a magnetic field, when the superconductor is in a temperature window of TC1 and TC2, which of course we are finding out through the experiments, these magnetic fields penetrate through the superconductor along certain lines or along certain points. And these form something called vortex lines, vortex core. And the beauty of this vortex lines is that the point where the magnetic field penetrates the superconductor, due to the Meissner effect, there is no superconductivity at those points. So the superconducting gap I mentioned here, it closes at those vortex points. So which means it just closes like this. And now I have a energy crossing at the 0, energy is equal to 0. And I can prop for Majorana state. I can try to do experiments to find Majorana states at those n equal to 0 points. But this is not very practical. This is not at all very practical, and it is not seen to happening. So they have turned their attention to a P-wave superconductor, which is a non-trivial superconductor. So in this kind of superconductor, there is something called the Bury phase coming into picture, and Bury phase can actually do something spectacular. I will say what that is. So in the case of vortex state in superconductors, what actually happens is there's a zero energy crossing, but however, you cannot find particle in the zero E equal to zero state in reality, in practice. Why? Because there is something called 0 point quantum energy, 0 point quantum energy, and this is something which appears in the quantum harmonic oscillators also, because of the quantum fluctuations at let's say at very low energy, in a very low energy state, because of quantum fluctuations, because quantum always have uncertainty associated with it, right? So there will be a 0 point quantum energy, and because of this energy, we cannot find exact E equal to zero state. It's not possible to pinpoint. This can be circumvented by using a P-wave superconductor, which is having a property of Bury phase in it, which cancels out the 0 point quantum energy, and thus we can observe Majorana bound states in such materials. And now the concept of Bury phase is quite interesting because it draws an parallel with another interesting concept in the classical case. Just sometimes we say common sense is not very common. So here we see that if I hold up a let's say a pointer at the North Pole, let's say in the Arctic region, I hold a pointer in a particular direction, and then I walk from the North Pole down to this point here, and still I hold my this particular pointer along the tangential direction in this way, and I go here, and still I have my pointer in this direction. From here, I change my direction. I go along the latitude, and I come here. I do not want to change the direction of this pole. It will remain in the same direction, and I come here. I only change my motion, my direction, but not the direction of the pole or the pointer, and then I retrace back towards the pole. And now, interestingly, when I reach back the pole, I find that from a global perspective, that this particular pointer has changed the direction altogether. Some angle theta has been subtended after I made this kind of a transport. So the simpler way or mathematical way of saying this is when I traversed a closed path here on the surface of the sphere, the I picked up a phase of theta. I picked up a phase, and now this phase has an analogy here in the condensed matter systems. It's called as Bury phase. Now, how do we understand this? So from the normal time-dependent Schrodinger equation, time-dependent Schrodinger equation, TDSE, we know that IH cross del psi by del t is equal to H cap psi is the time-dependent Schrodinger equation. So the physical systems, the quantum physical systems are described by within the wave mechanics mechanism introduced by Erwin Schrödinger in the 1926, right? So he had formulated this particular equation where we can express the energy of any physical system, which is written as get psi in this form IH cross differential of this get psi. This is get psi with respect to time. So this is a partial differential equation. So del psi by del t, because psi is a function of both position x and t. So I don't want to touch the position part. I'm only differentiating the time part, del psi by del t. Now when I write like this, psi can actually have a phase and an amplitude. So that is written here, n of RT and here n of t and e to the power of minus theta t. So n of t is the amplitude and e to the power I t theta t is the phase. And now when I differentiate with respect to del by del t, it will have a chain rule of differentiation because both of them are dependent on time, the amplitude and the phase. So I have two terms here in the second step where the first term I differentiate with respect to the magnitude, and then the second term I differentiate with respect to the phase, d theta by dt. Now I want to express the theta in terms of other parameters. So all the three have e to the power minus theta as common, so I cancel out them. All these three are cancelled out, and here I express the energy here En, because we know that IH cross del psi and T, it will be En, right? And it will be written as IH cross. Okay, so what I did here, I have multiplied on both sides with a bra and T, right? Which is the conjugate of the ket. And when I did that, so here from this equation, if I multiply it with the bra, so here I take bra psi, and then this here also it will be bra psi, and that results in, that will give me the energy, the expectation value, or the energy expectation value of the Hamiltonian, which is the energy of this particular state. Okay, so anyway, what I did from here to here is taking conjugate of the ket vector, multiplying it on both sides, and thus I get energy in terms of these two terms here, IH cross nt d by dt nt plus h cross nt d theta by dt nt, and then I express theta in terms of other parameters here. So when I express that, then theta is equal to 1 by h cross integral of en dt prime minus I times n of t nt d by dt nt dt. So the first term here is the dynamical phase, which is due to the change of energy of the system with respect to time. However, the second term is what is called the Bury phase, and that is because of the transport of the quantum state in the parameter space. So we can express the second term in terms of the transport vector, the r, or rather the position vector r, and we can express it like this: closed integral of n of r del r n of r dot dr. Now this is a familiar form where a vector dot product with a differential vector dr, and which can be converted to a form of an integral of our bounded area dot product with the curl of that vector. And similar to what we do in the case of magnetic fields, where we have magnetic field B, and by we can express it in the form of the magnetic field, the vector potential, magnetic field vector potential. Right. So in the same way, we have a particular Bury phase, which can be expressed as integral of ds dot bn, which is the flux, not because I have applied an external magnetic field to the system, but because of the parallel transport of or rather the uh, the change, the phase picked up by the quantum vector when it was transported through some positions. The phase it has picked up, that is encoded in the Berry phase gamma, and it has consequences in the form of cancellation of the 0 point quantum energy, because when I have an electron here, and I have um, let's say I have a some kind of an impurity or defect here. Now when this electron comes and it hits, it cannot go this direction, so it will go around it, right? It may, because of the inertia, it may come back here. And now if this is a like a magnetic impurity, let's say, uh, or maybe if it's a non-trivial case, like the material has non-zero Berry phase, then the electron, when it reaches back, it would have picked up some phase. And if the phase is equal to pi, then it would cancel out the wave amplitude of the electron. That means the electron will interfere with itself, that the wave interferes with along with it itself, and thus it cancels out, and thus we will not be able to see the electron coming out. But however, if the electron has not pi, some other non-pi value, then it would have a non-zero amplitude, and we'll be able to see the electron. It will not cancel out. So the same way, the topological, or rather the p-wave superconductors, they have such a non-zero Berry phase associated with them, and as a result, we will be seeing the existence of Majorana particles in such systems. But however, such to find such systems in practice is very difficult. They're very rare to be found in nature. So how do we implement this idea is using the materials which we have, and that is with the help of a nanowire. And how do we make this nanowire? We make this using a semiconductor, and we put this semiconductor on top of a superconductor, because we know that Majorana bound states can be formed on only the superconductors, right? Because of the particle hole symmetry. So semiconductors do not have the potential to show Majorana bound state. So when we bring this semiconductor close to the superconductor, there is a chance that we can see Majorana fermions or Majorana bound states in the semiconductor due to the proximity effect, such as in this circuit here, or in this device here. We see that in these two ends we have the Majorana pairs formed, and they are spatially separated to the two ends. Now, why this kind of a structure is favorable? Because if there is an environmental interference against this particular Majorana bound state, and tries to perturb its energy to some non-zero value, it will not be able to do so, because its counterpart is sitting here, and it is at zero energy state. So shifting from zero energy state means it is strongly entangled with the other one, so it cannot shift from the zero energy state. So the environment, by accessing a partial portion of the system, cannot introduce errors into the system, right? So thus it has a topological protection associated with it. That is how it is able to have a topological protection and a strong error correction, which is inbuilt in the hardware framework itself. So now what Microsoft did was they used INAS, indium arsenide semiconducting nanowires, and they grew it on top of aluminum, which is an S-wave superconductor. And so it is not an P-wave superconductor, rather an S-wave superconductor, which is trivial, and it does not have any special properties like we see in the case of p-wave superconductors. So in the um, in a interface between a superconductor and a metal, let's say this is a metal and this is a superconductor, and we have some barrier over here. So in the superconductor, the charge carriers are basically the Cooper pairs, which are coupled pairs of electrons, right? And they form a condensate, a coherent condensate. And as a coherent condensate, they undergo lossless transport, which gives the superconductor its zero resistance state. And however, if I bombard a superconductor from metals uh, by applying some voltage to the to a structure like this, where I have metal on one side and the superconductor on the other side, then the electron, when it reaches the boundary or the interface, it tends to reflect back because it cannot enter into the superconductor, especially if the energy of the electron is low. In other words, if the energy of the electron is less than the superconducting cap. However, if I increase the energy and if I uh, pass the electron or pass the current in a higher energy state that is larger compared to the superconducting energy gap, when such an electron is bombarded at the interface, then the superconductor will allow this electron to go through it in the form of Cooper pairs, because it does not have single electron transport allowable in it. So Cooper pairs will flow in the superconductor. But this is a violation of the conservation, because I sent only one electron, whereas there are two electrons in the form of Cooper pairs which are transported in the superconductor. So now, to compensate that, there will be a reflection of a hole. So this is electron, the filled circle, and I'll have a reflection of a hole which will come back. And this particular phenomenon is called an anti reflection, which describes the transport behavior of metal superconductor junctions. And it also can be experimentally traced by using a spectroscopy called conductance spectroscopy, where we apply a voltage, a bias voltage here, and we scan through different bias voltages, and we find that at a particular window of this voltage bias, the conductance of the system, or conductance is the inverse of the resistance, and that is very low. In fact, it is proportional to something called T square, capital T square. And if you had guessed right, T stands for transmittance, which means the electron getting into jumping from here to here. It's the transmittance of the electron. And if the electron is able to transmit 100%, all the electrons I sent, they are all able to go through, then it has a T equal to 1 value. But if only some of the electrons are able to transport to the other side, then the T will be less than 1. But however, if in the case of electron having a low energy, this electron, it will enter the barrier here, and then it reflects, and then it comes back. So there are 2 times electron entering this barrier. So one time it enters with a transmittance T, and another time it enters with it goes back with a transmittance another T, right? So 2 times it performs these 2 operations, so T square. So hence this is T square within the delta band gap, this delta band gap. However, if I increase the energy value of the electron, it has it enters into this state with the transmittance T, and it does not reflect back. Hence, these are proportional to capital T. So if I do a scanning of V bias, the voltage, I will get a state such as this. So I'm just filling the gaps here. I'll get a state such as this. Now these two peaks are because of the resonant nature of the system. What we need to primarily focus is these three states, which follow the relation of being proportional to that transmittance in these two regions, which are beyond the superconducting gap. And within the superconducting gap, it is low, because t square of a value below 1 will be always less than 1, much less than 1. So it is at a lower energy here. So this is the conduction spectroscopy, and this is the signature of an electron being sent to interface, or current being sent to or a current driven metal superconductor interface. So in the under normal conditions, under ideal conditions, we have quantized conductance value of 2 e squared by h for these conductance values. However, due to non-ideal situations, we don't find that quantized conductance. It will be lower than that. So this is an experimental, real-time experimental data shown here, where we see there's resonant behaviors um, at the at the gap values, and then it relaxes to some higher energy values, higher conductance values, and you have low conductance values at the within the superconducting gap. Now, interestingly, and yeah, so there are so many traces which you can see. The bottom one is the trace corresponding to a magnetic field of 0. Okay, magnetic field of 0. But when I increase the magnetic field, interestingly, I see that there is a hump, a small hump being formed exactly at equal to 0. So now for the system which we discussed, that is the nanowire on top of superconductor, we apply magnetic field, and as we increase the magnetic field value, I am seeing the signature of a zero bias energy, ZBE. And now this is a potential signature that your system consists of a Majorana fermion, because Majoranas exist at the zero energies, right? And hence, if I have a peak here, that is a signature of Majorana MBS. However, there are some certain other debates and shortcomings. Things like the zero energy state can also arise from the non-ideal um, nature of the material. It could be due to other effects also. So there's no strong ground. It's not well established in that way. However, the Microsoft's invention, they have been like very confidently on the side of that this belongs to a Majorana bound state. Indeed, further experiments and uh, verifications are to be done to conclusively determine that these are topological qubit states which are formed of Majorana bound state. Now, if I have a Majorana fermion or Majorana bound state, how do I do the gate operations? How do I measure them? So that is something called a braiding operation. So if I have a system such as this, in which I have a set of Majorana bound states, and I have one topological qubit. This forms a one single topological qubit with 4 Majorana bound states, and I exchange these two particles. So okay, so one of the fundamental concept here is that if there are two quantum particles and I exchange their position, what happens to their wave function? is of fundamental interest to the quantum physics community for a very long time. Suppose these particles are bosons like photons and phonons and etc. And we exchange two of them. Then the wave function of that particular quantum state will remain the same. It will not change because I'm just exchanging two particles from their positions. It will not change their wave function. But if I exchange two electrons, because the electrons are fundamentally different from photons, they are called fermions. And when I exchange the electrons, the wave function picks up a negative sign. So the psi becomes minus psi. So this is the antisymmetric property of electrons. They are called fermions. Now, what is negative? Minus means e to the power I pi, right? Which means that when I exchange two electrons, the electrons picked up a phase of pi. It picked up a phase of pi. However, if I exchange two Majorana fermions, they have the potential to pick up an arbitrary value alpha as the phase, which means they do not have to be either pi or in this case e to the power I0. They can be between 0 and pi. Alpha can be 0 and pi. So when I do a braiding operation such as this, where I exchange two Majorana particles, so my final psi state can be written as B12 into the psi initial. Okay, this is psi I and this is psi F. So B12 contains the information about the phase change, the phase information e to the power I alpha. So I can implement quantum gates such as Z gate using this particular way. This being the time direction t. So I braid two Majorana particles and I get this state. And then I again braid them and I get this state. And this is a Z gate, in the quantum Z gate. And now if I need to do an X gate, so I have 1, 2, 3, and 4 quantum Majorana particles, and I braid these two here in this way. And this one I again, yes, so I braid these two here. So now you may ask, these two look the same. What is the difference? Now the difference lies in how I have initialized these particular Majorana particles or Majorana bound states. And that information is contained in this B12. So here I get psi f. My final quantum state will be equal to B23 into psi I. Okay, so this 2, 3, 1, 2 represents the numbered numbers 1, 2, 3, and 4. So here I am braiding the 2 and 3. So this coefficient here, it is B23 or the matrix containing the phase information. So now, I can give a little more insight into this. Suppose let's say I have my B12 in this particular representation. B12 is equal to 1, 0, 0, and I. And some phase factor associated with this, e to the power minus I pi by 8. Now if I apply the B12 two times, B12 square. So what do I get? What do I get? What I will get, it will be equal to a Z gate. And what is a Z gate? We know that Z gate is equal to 1, 0, 0, and -1, right? This is the matrix representation of Z gate. Now, try this out for yourself. Square this matrix, and you'll surprisingly you'll see that it is same as a Z gate. So this is how the braiding operations of Majorana bound states help us implement different quantum gates, such as a Z gate, X gate, and for your information, B23 can also be squared, and we can find that it is same as the X gate. And B23 representation of B23 is as follows. I find 1 by root 2. So 1 minus I and 1. So if I take a square of this, then I find that it is equivalent to X gate. So this is a bird's eye view of the Majorana bound state based qubit computation. However, we can still get a little bit of understanding by working out these states and these calculations. And this is an evolving field, so it's a very new, and so it will not be as easily graspable like the other implementations, like the superconducting qubits and so on. But the potential and the future of this particular implementation is so bright. So I wanted to share these things, and I'm sure that this field will evolve much faster, and it will have promising results in the future. Okay, so with that, I have completed the Majorana fermion or Majorana bound state implementation, or the topological qubits, which was recently found out and trying to implement and make it commercial by the Microsoft company, and we hope it will come soon. On the other front, the research conducted on quantum computing are plenty, and countries like China, US are at the forefront, whereas India, I can see, is in the third spot. And it just shows the amount of significance, the potentiality of quantum computing in the present day scenario. 44 years back, one of the great stalwarts of physics, Richard Feynman, he had envisioned such a future where quantum computers or principles of quantum mechanics will be leveraged to create quantum-based computers, which may not actually replace the classical computers, but it will certainly complement the classical computers in a way that is very different, and help us solve some of the complex problems and that we have today. So he said, by golly, it's a wonderful problem because it doesn't look so easy about the quantum computers. And not only that, it itself is not so easy. And we have seen that 44 years down the lane, this field is still evolving and still not complete. He also mentioned that we can perform simulation of nature through the quantum computers. So let's say if I have a classical computer or an HPC, high performing computers, I can easily model and solve problems of two electrons. And if I have increased the complexity, 3 electrons, 5 electrons, still I will be able to solve with a little bit of overhead. But if I increase the number of electron counts to, let's say, 30 electrons, for nature, 30 electrons is nothing. And we know there are about 10 to the power 21 electrons in silicon semiconductor. Okay. Yeah, I'm going to share once again. Yeah, I hope it's visible now. Thank you. All right. So Richard Feynman had a vision back in 44 years back that such a quantum computer can be used to simulate um, the nature itself, which contains plenty of electrons in it, not just 30 or 20 electrons. So that is what about quantum computing. He also made another statement. He said there's plenty of room at the bottom, which actually was meant for the field called nanotechnology. And this is a field which has complemented our endeavor to make a practical quantum computing device, or at least 100 odd qubit quantum microprocessors, because of the advances we made in the nanofabrication technologies and the ability by which we can pick and control each atoms. Like I have shown in the last class about the TEM, where each electron in the silicon can be imaged and can be analyzed. So these two fields together, they form the backbone of our endeavor for quantum computers. And following his lead, people like David Deutsch is the father of quantum computing. He had come up with quantum algorithms back in 1980s, where there was not even great advancement in the classical computers. And also other people like an Indian origin, but a scientist named Vazirani. So he was able to also contribute algorithms, Bernstein-Vazirani algorithm, which was meant to clear the foundation aspect of quantum computers, where we have algorithms that can significantly have advantage over the classical algorithms. And when the quantum computing hardware is ready, we can implement this in a more hardware efficient way and get the results. So in that connection, the dream of Richard Feynman was to may have a quantum simulation using the quantum computers, right? So we have a quantum system, and we use a quantum computer to simulate those quantum systems. And one of the key areas where this is being used is the optimization problems. So we have Hamiltonian of the system, E psi, right? Internet. All right. So this can be taken. You can take an expectation value of this equation. This is the famous Schrodinger equation. And if yeah, so this psi is a ket psi. This is a vector ket psi. And this is a matrix H. I act this H on this vector. And as a result, I get eigenvalue E, eigenvalue of this matrix H. and the column vector psi ket psi. Now I multiply both sides by the row vector or the bra psi, and then I have bra psi h ket psi. What does it do? It will just act on this one. E is a scalar quantity, so I can take it out. E times the inner product of psi, which is nothing but it's a unit vector. This will be equal to 1. And thus I will be left with the E. E is the energy of the system. So how do I find the energy? By sandwiching the energy operator or the Hamiltonian between the two sides, bra psi and ket psi. And that can be written as like this, angular brackets H, and that will be greater than E0, E0 being the ground state energy. And this is a particular, this is a specific recipe you can use for as a cost function to solve this optimization problem. And here we approximate the quantum state vector using a parameter theta, where theta represents the rotation angle or the phase which we talked about. And by optimizing the psi, we will be optimizing for this theta, we will be able to calculate the energy and then narrow down and then optimize it and find out the optimal theta where the energy is a minimum. And thus we will be able to find out a ground state energy level of certain molecules or systems, such as, let's say, H3 system or hydrogen's H3, where I have 3 hydrogen atoms in a lattice like this. And I wanted to find out the minimum energy of this state. So how do I do this? I need to first find out the Hamiltonian of this system, which is the energy operator. And then for that, I need to know the distance between these two atoms. And with those information, I need to find out the Hamiltonian, and then I need to parameterize my psi vector, which is the eigenvector of this Hamiltonian. So Hamiltonian will be a matrix, right, with some values A, B, C, D, let's say, and then it will have an eigenvector associated with it and an eigenvalue. And then it will not be that easy. In fact, I will not be able to exactly find out the eigenvector for this particular Hamiltonian. And that is why the problem is very hard. And I need a quantum computer to solve it. So I approximate it with some theta value. And that educated guess of the state is called an ansatz. And then I calculate the energy using that particular ansatz, and then I pass it to an optimizer. So I'm coming from here and then I go to the optimizer. An optimizer is a classical system or classical computer which optimizes it using some classical methods like the gradient methods, and then it will send back the result to then it will find the theta value. It will have a theta, it will move to the next theta, like theta I plus 1, and from theta I goes to theta I plus 1, and then it passes this information to our cost module, which again calculates a new psi, and like that. Finally, we will optimize the whole thing and we'll come to a particular theta value where the energy is the minimum. So to do this thing and to do this in a quantum circuit, we cannot give the values of Hamiltonian directly. So we need to map the values of Hamiltonian in a quantum compatible way. And so to do that, we have to take the help of second quantization formalism. And by the way, this whole algorithm is called as variational quantum eigensolver, or VQE. In the second quantization formalism, we express the parameters in a Hamiltonian in the form of C and C dagger, where represents the creation operator and C dagger is the annihilation operator. So if we can express any system, any Hamiltonian of any system in this formalism. So so what we can do here, I can show a simple example here how we can do that. Sorry. Okay. All right. So, so I'll just show you the layout of this particular algorithm. So yeah, so this is how it is being done. So first, this is a case of a 2-qubit system. I have a 2-qubit uh, system, and we know that a 2-qubit can be operated upon by operators of 2 by 2 matrix representation, such as this. So yeah, 2 by 2 matrix representations, right? So I am passing two qubits, get 0 and gets initialized into get 0, and then I encode them with a particular method. So basically, this is where the point where I do the encoding is where I convert these states into the quantum compatible way, into the quantum compatible way. So yeah, so I can express my psi, the wave vectors psi, in terms of the Slater determinants. So I have square root of n, and there will be a Slater determinants where determinant which consists of entries like this, chi 1 to chi n, and I have chi n of xn. So I and this is chi n of x1. This is chi1 of x1, where x1 represents the position and chi n are the atomic orbitals of each of the n particles. Okay, so every fermionic wave functions get psi can be expressed in terms of this particular Slater determinant, and it follows the rules that govern how the fermion wave functions change sign upon exchange of two particles, and so on. So we can express it in this way. And now this particular chi1 to chi n, we can also write them in this particular way. Get get n1, get n2, so on, and get nn. So this is called occupation number basis, where I have n particles, and these n values, n1, n2, nn, can either have 0 or 1. If it's 0, it means it is there is no electron, or there's no electron in that particular state. And if it is equal to 1, it means there is an occupancy of an electron in that particular site or state. So that is what the occupation number basis is actually. So we are trying to encode this to the 2-qubit basis, 2-qubit inputs which we are giving here. So this is similar to what we have seen in the multi-qubit systems, where we have a 2-qubit system can be written as ket 0 0 or ket 1 1, right? So yeah, I will just so I can express my wave function in the form of the sum of all the particles within the system, and Ci stands for the creation operator, times the ket n1, n2 till nn. So this means I'm trying to create a particle at the site I. Okay, so here I have ni here somewhere. So I create that that particle, and I sum it for all the particles, and that is my wave function, where I have an electron at every n particles, n sites, right? So after I perform this encoding, what I get is a wave function, a 2-qubit wave function, which I denote as phi ref, and then I pass it on to the ansatz preparation. So here, the ansatz preparation, my Hamiltonian is in a particular second quantized form, right? And now using some mapping, such as Jordan-Wigner mapping or parity mapping, I will transform my form of my Hamiltonian into a form where there are Pauli Pauli X operators, Pauli Z operators, which are identifiable to the quantum circuits. So that is where I have this ansatz preparation in this one. In ansatz preparation, that's what's happening. And I also I also convert my state with the parameter theta. I put theta into my wave vector, and then after that I measure it. And I get some value of the energy, and this energy value is then passed on to the optimizer, right? And then it will calculate a new theta value after it identifies the error in the energies. So there will be a target energy, and because E0, we know the E0 value, and so it will find the error, and then it will give a feedback of the updated theta value, something similar to what we have seen in the neural networks, where the optimizer does helps in the back propagation through different layers. But here it just gives a feedback in this way, and the new states are calculated. And finally, when the error is very less, it will be able to output energy, the ground state energy of the molecule. So an example for this is a Hubbard model where we can express the Hamiltonian in this form. H equal to T times sigma C dagger C plus U times Ni up, Ni down. So we have uh, uh, a sequence of electron like a 1D chain, and an electron from this can jump to this particular state. It may be a vacancy here, and that is represented by a strength T. And here the creation operator acts, this is defined in the Hamiltonian in the form of a creation operator acting on this side, and an annihilation operator acting on this side. So together what we have is a T times C dagger, or T times C dagger C, which is the first term, or it's called as a hopping term. And this is if the T value is very high, that means the chances of hopping is more, and thus the electron can transport more through the system, and its conductance will be more. And the second term is Hubbard U interaction term, where we have the number state like Ni up and Ni down, corresponding to the up spin and down spin electron. Like in the case of two sites, let's say I, these are I states, and you have an up spin here, let's say, and there will be a repulsion between these two states. It is represented as U. U is the Hubbard or the electron-electron interaction, and we can represent this in the. You can map this onto a quantum circuit with the help of a mapping called Jordan-Wigner mapping. And in this Jordan-Wigner mapping, we convert this annihilation operators, annihilation creation operators, as well as the number state operators into Pauli gates, and implement it in a quantum circuit. Okay, so one of the ways by which we can perform this mapping is something like, let's say, I have um, I have my creation operator here. Let's say it is at the site P, which is an arbitrary site, and I transform this in this way, half into xp representing the x gate, plus I times yp. Yp is a Pauli Y matrix, and then the z gates are represented as follows: z1, 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 z2, so on till zp minus 1. So we apply this to every p side of this Hamiltonian, and we get Hamiltonian expressed in terms of x, y, and z, which is which can be implemented in the quantum circuit. All right. So yeah. All right. So that is about the VQE. But there are other optimization which can be performed using the quantum computation, like the QAOA optimization algorithm. And recently in London, these quantum algorithms of optimization were used to perform the timetable scheduling of the trains that arrive at a station, a London Bridge station, and they were able to successfully implement this over a period of 8 minutes. They were able to schedule the arrival departure times of 26 trains, as well as um, schedule um, their station time. And so these two kinds of scheduling, they were able to do timetable scheduling as well as arrival departure scheduling. And this they were able to do this with 103 qubits architecture, quantum architecture. So we might think that this is an easy problem to handle, because uh, over the world there are plenty of rail stations and trains, and timetable scheduling must be quite easy. However, these kinds of problems scale up very quickly. Like a case of 26 trains over an 18-minute period is something which is not very common in the world. So this is because of the extreme busy nature of this station, London Bridge Station. And to handle such situations, we need to have an efficient optimization algorithm. And classically, it is very difficult to perform. It is equivalent to the case where when I have 5 electrons, I can simulate using classical computers. But when it scales up, it becomes increasingly complex to simulate. So this is a use case where quantum computers are handy in solving a real life problem. Similarly, we have another scenario here where the navigation of airplanes from a starting point to their destination. So normally, the airplanes use the GPS, which is aided by the satellites. However, the satellites are not very helpful when we are in very in the outer space, or in the deep waters. So we need to have a GPS-free alternative to navigation systems. And recently, there has been implementations based on quantum inertial sensor, where they used an atom interferometry principle to perform this GPS-free navigation, and its sensitivity is pretty good. And not only that, it has got a good durability and accuracy too. And the research of this, although there have been a few implementations and practical in certain airplane flights, the research is still going on, and these countries are at the forefront of this particular GPS-free navigation, quantum-based inertial sensor navigation. And companies are also trying different tests to on this particular use case of quantum computing. Rather, it's quantum sensors. And some of the recent achievements in the field of quantum are specifically quantum communication, where a team of DRDO and IIT Delhi were able to demonstrate a distributed entanglement communication for more than 1 kilometer distance and through free space. There was also a quantum key distribution network implemented by the European project Secure Communication based on quantum cryptography. Also, advancements from our neighbor. There's been a launch of a satellite and a QKD installment link between Beijing and Shanghai. So these are some of the advancements in field of quantum communication. Germany has also recently has been making breakthroughs in a field called quantum battery, which also can boost the solar cell efficiency, and it seems to be like more durable, just as in the case of the GPS-free quantum sensors using the atom interferometry principle. So as you can see in this headline here, 30 kilometer teleportation has been achieved over the internet for the first time. So there have been advances, and very recently, so there have been advances, but the main issue plaguing this quantum advancement is that of integration of large number of qubits, because as we have seen in the case of Deutsch algorithms and other algorithms, we also use a set of ancillary qubits along with the main qubits, which we are using to perform the computation. So when the space taken by these ancillary qubits are not small when we are scaling up, right? And also errors in the system can distort the result. To avoid that, we set aside certain number of qubits to perform this error correction. And in the case of communication, we also set aside certain other qubits for detecting corruption of the data by some third party. So we need a lot of qubits to implement a real time a practical quantum computer. And for such a high integration comes with complexities, and uh, such as the bulkiness and the interconnect scalings, and so on and so forth. Okay, yeah, I'm back. Sorry for that. Share again. Yeah, so we are about to end. So a couple more slides. So very recently, Google has come up with a Google Below chip, um, which was having a below threshold quantum error correction. So it means that as the system scales up, normally the error gets increased, but in this case, the error reduces as the chip scales up. And the one of the key point of Google Willow chip is that even it's which took 10 citrillion years in the which NISQ stands for noisy intermediate scale quantum. So noisy stands for the errors that creep into the quantum chips that are currently which we have. And so we are not yet free from the noise incorporation. And intermediate stands for so far we have chips that can reach up to 100 qubits, and the potentiality for reaching up to 1000 probably by 2030 or something. But however, we need for practically solving complex problems, we need millions of qubits, and present capabilities does not let us do that. So hence we are at a stage of intermediate scale, and that is why we are at the in NISQ era. But our goal is to reach an FASQ era where we have a fault tolerant application scale quantum. So this terms fault tolerant, which means that the error does not impact us so much, impact the computing. And also the application, it should be an application scale level, which means there should be millions of error corrected qubits for the system. And such a quantum computer should have ideally an error rate of 10 to the power minus 12, uh, which is drastic improvement from what we have today. Today we have an error rate of around 10 to the power minus 5. So the state of the art, we have about 2 dozen manufacturers and more than 40 quantum processing units currently. And the countries like United States and China, they lead the field as of now. And even in the Europe, there are about 4 to 6 commercial scale QPUs. And in total, over 160 QPUs are currently in the prototype planning or commercial stages, developed by close to 80 manufacturers across 17 countries. And most of the implementations are made out of superconducting systems, over 40%. And the future holds that we know that today the development of ML and AI, on the shoulders of ML and AI, the classical algorithms are rapidly improving. But there are certain classically hard problems which can only be solved by quantum methods. And for example, quantum dynamics, which is the time evolution of quantum state. So we had discussed about the Berry phase. There was another term which represented the evolution of energy, which is nothing but the time evolution of the quantum state, and which can be simulated in a quantum computer. And then we have a strong quantum chaos problem, which are also equally hard in classical, but can be done using quantum. And in the future, my take is that AI in collaboration with quantum will drive the future. And if that is so, the demand for the data will increase drastically. So with that, I would like to end session today. Can have a session of Q&A.
Okay, so I think again he has some network issue, have dropped the session. Fine, however, we are done for the day. So I just need to update related to certificate and all. I'll let you know. Before that, I request everyone, please mark your attendance without any fail. As you all know, 60% of attendance is very mandatory to get the certificate. The attendance link, which I have already shared it on a chat, I'll be sharing once again on the chat in both Zoom and YouTube chat. I request everyone to mark your attendance without any fail. As you all know, attendance link will be deactivate on 5:30. So before that, kindly mark your attendance. Okay. And as I told you all, the like 60% of attendance is very mandatory to get the certificate. So how you will get your certificate? I know you all have a query related to this. The certificate will be going to issue you to your register mail ID. Okay, whichever the mail ID you have registered for the same mail ID, we will issue the certificate. Those who are eligible of 60% or above 60% of attendance. Okay. So the attendance will be shared to you all within a week. Okay. I request you all to wait. You will all get the certificate within a week. Okay. Within a week or 10 days. Okay. I request all you have to wait. Okay. So I hope you all understood related to certificate. If any other queries, you can just ask me out so that I can answer it. Any other questions or query, you can ask me. I will answer it. I hope all this of 5 days is helpful for you all. We'll again meet on a different SDP or FDP program for definitely. So yeah, any questions to be asked, you can ask. The chat is open. I'll answer for it. We'll wait for 5 minutes. So if any questions, you can ask. And related to material and all the materials will be going to be uploaded in LMS dashboard. Please be waited by today end of the day or by tomorrow. All the materials I take from trainer and I will upload it to the LMS. You can access the materials and also recordings in the LMS dashboard. And one more important thing, some people they will watch the recordings and they will come back to us and asking for the certificate. As you all know, you have to attend live session. In the live session, whatever the attendance has been marked for 60, if you secure 60 or above 60% of attendance, then only you will receive the certificate. Madam, I have attended all the session and given the feedback too, but the LMS portal showing program as 0. Is there any problem to issue the certificate? Here consider on that. Yeah, so there is no issues. If it is in a portal, it is showing a different percentage, no issues. The main thing we will capture to the attendance, whichever you will mark it on a live session. Please share LMS portal link. Yeah, I'll be sharing it. Any other questions? Yes, I have shared the LMS portal link on the dashboard. You can use that. No, we won't conduct test for the faculty development program. We will be not conducting any assessment. So we are not conducting any assessment or something. Any other question? Okay, if any questions or any issues, you can drop a mail to edl@xlr.com. I'll just ping the mail ID on the chat. If any issues or any concern, you can drop a mail. Okay, as I told, I'm just repeating once again. Related to certificate, you have to secure 60% or above 60% of attendance, then only you will receive the certificate. The certificate will be shared for your registered mail ID. Okay, and the materials recording you can access in the LMS dashboard. And some are asking for the previous day's attendance link. Sorry, as you all know, the attendance link will be active only till 5:30. So yesterday's or previous attendance link can't be shared. Yeah, when will I get receive the certificate? The certificate will be going to issue within a week. You have to wait for 1 week at least. We will share your certificates if you are eligible. Okay, I hope you all clear. I'm not getting any questions to be answered. Any other questions? Yes, 60% means 3 days. Yes, if you have attended for 3 days, no issues, you will get the certificate. For any query, you can drop a mail to edl@xlr.com. Okay, thank you all. Thank you all for joining this wonderful session. I hope this session was useful to you all. Thank you so much for attending. Ma'am, speaker PPT is possible to. Yes, sir. This PPT will be going to be uploaded in LMS dashboard. You can access over there. Okay, thank you all. Thank you for joining. Have a great day. We'll meet again in next STPs or FTPs. Thank you so much for joining all these 5 days. I request everyone to wait. If you secure the 60%, for definitely you will receive the certificate. I request you all to wait for 1 week. Okay, thank you all.